So we're in chapter 3, which is chemical formulas. And basically, this chapter is going to be a review and an extension on how chemicals come together, how they form chemical bonds, why they form chemical bonds, and then how do we appropriately name them and write the chemical formulas for it. As you can see right here, there's 3 chapters that we cover. Primarily, we cover chapter 9. That's the most important. So that would be the chapter that you should look at first. Chapter 22 and 23 deal with organic. We'll do a little section on organic in this, but what basically the chapters in your book have way more information than we're really going to get to, because we're primarily in organic chemistry class and they cover a lot of organic. So this is good information and it would definitely help you, because in college you'll need it, or AP Chem, or AP Bio, but there's more than you need in these two. So this first one is just on the beginning and ionic. So when we talk about stuff, is the reason why we write chemical formulas and write chemical names is because they show us the actual atoms that make up the compounds. So we're taking these elements and we're putting them together, and we need to have ways to do that. So one thing that kind of makes sense to most people is that we have systematic ways of doing it so that everyone agrees. So it's kind of like learning a little language, and once you know the rules of the language, it's not hard, but if you don't know the rules, it can get really confusing. And again, we write formulas because they tell you the kind of the atoms and it tells you the number. So that's also useful. Like if you're digging up precious metals, they're in ores, and they're primarily found in other minerals. And so what you can do is you can see, okay, what has the most copper, what has the most zinc, and if that's what you're looking for, then the formulas become very important. So most of this chapter we're going to be looking at inorganic compounds, and those are the ones that basically don't contain carbon. And when we say don't contain carbon, we mean like large chains of carbon. And this first section is just on these ionic compounds. So there's ionic compounds, there's covalent compounds, there's acids, and then we'll also look at organic. And when we have ionic compounds, this is really important, and again, this is in your book as well, you should be reading. It's a lattice, so it's an actual crystal structure of cations, which we know are positive, and anions, which we know are negative, and they're held together by those electrostatic forces. And when we say electrostatic forces, all that means is the positive and negative. So we know that opposite charges attract, and that's this electrostatic forces. And an important thing about ionic compounds is they are going to work to form neutral compounds. If they are not neutral, that means that they don't have stability, and if you're not stable, you're not going to really exist chemically. So when you're balancing charges and stuff, that's why you're balancing charges, because it allows the crystal to be stable. When you're doing ionic compounds, you typically, not always, but mostly have one metal, and the metal is usually the cation. And then you typically have a non-metal, which is your anion. And again, there are things called, we have polyatomics and stuff, which we'll look at, but we're just talking generally, that's what we're looking at. And when you do this, when you put it all together and you write your chemical formula, you are making a formula unit. And that's your simplest ratio. So just real simple, quick, you just want to make sure you understand that there is a difference between a crystal lattice and the formula unit. So your formula unit would be this guy right here, and that would be your formula unit, if it likes me. And then the whole big picture is your crystal lattice. So when you're writing your formulas, this is what you'll be doing. Your formula unit is going to equal your chemical formula. So you just want to keep that in mind, that you're doing that simple thing, but ionic compounds do form these crystals. Sort of like, it's not the same, but it's very similar to like if you've ever made rock candy and those kind of crystals. And you can look at them from that. Couple simple things about our actual ions is we're going to look at just monatomic ones today. We'll look at different ones later. Mono means one. So this is an ion. And remember, if you're an ion, you have a charge. And you can be positive or negative, and you're making it from a single atom. And again, remember, everything with chemistry is basically because of stability. So when atoms gain or lose electrons, they're doing it to be more stable. And again, they're trying to be more like the noble gases, because the noble gases are inherently stable. So they're trying to become more like that. And we have an example here of metals. And you may want to write down metals hold electrons loosely, which means it's not such a big deal for them. Nonmetals typically hold electrons tightly. And if you think about that, it makes sense then that metals tend to lose electrons and nonmetals tend to gain. And again, that means that metals tend to be positive. And down here, nonmetals tend to be negatively charged. And again, we're not saying that nothing could ever happen, that you couldn't make them opposite. It's just if they have their way, this is what they would like. And you can see here we have sodium. Typically has 11 electrons. It typically loses an electron and it's down to 10. And you can see it's much smaller because it lost an electron and it is positive. And then we have here chlorine. It's kind of backwards here. This is chlorine with 17 electrons. And he gains an electron to become 18. And you can see he's negative, and then he is bigger. Real simple, when you look at your ion sheet, and you do get the ion sheet for your quizzes, for your tests, all that kind of stuff. The front, you're primarily going to find your cations, so you may want to write that down. Front of your ion sheet. And when you look them up, they're going to be very simple because it's just the actual element's name. So when you're looking up Li+1, it's literally just called a lithium ion. So it's not anything different or fancy or anything. If you look up Mg+2, it's a magnesium ion. And good old Al+3 is an aluminum ion. So they chose this so that you always know that if it's just the element's name, then it's a cation, which means it's positive. So you can quickly tell that from the naming. On these guys, the anions, they are typically on the back of your ion sheet. And you'll notice that these are different. They end with something different. And again, they end in IDE. And this is to show you that it is an anion, that it is negative, and it's different. So this is the first thing that people kind of get tripped up on. But you have to be aware that when you do this, when you look up F on your ion sheet, which is on your back, you're not going to find fluorine. You are going to find fluoride ion. And again, instead of oxygen, you find oxide. And instead of sulfur, you find sulfide. So it's like the first clue to kind of tell you that, hey, these are different. And it's the first way that they try and give you a hint. Again, if you don't know the hint, then it gets a little harder. But you want to make sure you're paying attention so you can do that. So the real thing that we're going to do for this section is you're going to do the binary compounds. And again, binary means just two elements. And you're only going to do monatomic ions. So the ones we've been talking about. We'll deal with polyatomics and everything later. Remember, your positive charges are going to equal your negative charges. And you can stop the video, maybe discuss it a little if you want, of why you think it's necessary. And then when you come back, we'll put some things up about why. And again, these binary compounds are typically a metal and a nonmetal. So I'll give you a little bit of time if you want to discuss why you think they need to be neutral. And then again, like I said, we'll go over some of them. Alright, so just some of the reasons. The neutrality makes the compound more stable, is probably the major one. Some of the other reasons that you may have seen is just to balance out the charge. And there may be other reasons too, and you're welcome to put them up there. But those are the biggest things. Again, it's the stability of what you want. And again, this should be easy for you. This should not be difficult. This should be almost a review. So this first one here, these are the steps you do. You find your symbols. And again, you write your cation first. That's why they're in the front of your ion sheet. And then you're going to figure out, okay, what's your lowest common multiple? What's the lowest thing they can both equal? Keeping in mind your cation is going to be obviously positive. Your anion is obviously going to be negative. And then just check to make sure your subscripts are as simple as they can be. And we'll look at an example of that. So if we're looking at this, first example, we have lithium sulfide. So when you look up lithium, the first guy, he's on the front, and he's Li plus 1. And if we look up sulfide, he's on the back. And be careful, because there's all sorts of ones on the back that are polyatomics. But you want sulfide, and that is S minus 2. If you think about your lowest common multiple, the lowest thing that they can both equal mathematically is 2. So lithium would equal plus 2. And the lowest thing that sulfide could equal is minus 2. So then you just have to think, okay, how many of each kind do I need? And what you're doing, let me just undo this, is using subscripts to indicate that. So you say, okay, what times plus 1 can give me 2? And it's not hard mathematically. So what that you're going to use is just subscript to show you I need 2 lithiums to make the overall charge plus 2. For my sulfur, it's already minus 2. So technically we're multiplying it by 1. But we don't need to write that. It's not necessary to actually show that. So you just can leave sulfur as is. And then the third step for this guy is kind of already done, because that's as low as it can go. And what I mean for this step up here is, say we had something like this. What I mean for this last step is simplify the subscripts, is these are both divisible by a number, and basically what it means is they are not as simple as they can be. So what we mean by this is, if say you wrote something like this, that's technically balanced, because you have they equal the same number of positives as negatives, but that's not what we want. So what you would have to do is simplify it down. You divide both by 3, and you would get the Li to NS. So just, it doesn't happen. It shouldn't really happen, but if you do it, you just want to make sure. And here we have antimony 3 carbide. When they give you this Roman numeral, we'll look at this at the next slide. Just to make sure, though, this is telling you, it's telling you its charge. It's telling you which antimony to look up. So when we look up antimony 3, he's Sb plus 3. Carbide's on the back, and he is C minus 4, which means our lowest common multiple is 12. So what you do is you say, okay, what do I have to multiply antimony by to equal 12? And you should say, hopefully, 4. And then you do the same thing for your carbide. What times minus 4 will give me, like, add up to negative 12. And that means we need a 3. Step 3, remember, you check to make sure it's already as low as it can go. There's nothing we can do. So we are done.